Okay, hello and welcome to Lab 5. So this one's going to be a fun one. It is all about tic-tac-toe, believe it or not. So let me switch to the slides, and the idea is you're going to make an artificial intelligence that plays tic-tac-toe. I've done most of this for you, but you will do some of it, okay? Not a whole lot of code, but a lot of thinking. Again, it's one of those labs. So it will play tic-tac-toe, and it's all about trees, okay? So we're going to represent the tic-tac-toe game using a tree. What I'd like to do first is review binary trees, which is something from CSCI 41 that we go over, so that I can then talk about like how we can generalize this to a tree with a whole bunch of children, which is what we'll be using in this lab. Okay, so yeah, binary trees are just a bunch of nodes. They don't have to have any order, but you can have binary search trees, of course. And then they have children. Maybe they have left and right. And like, I don't know, 43, 88. This is a binary search tree, but it's still a tree. Okay, I could put 100 over here and it's still a tree. But might as well make it a binary search tree. So yeah, there's just a bunch of nodes. This is the special root node, right? And then we have children. For binary trees, we have left and right children. Okay, so this is the idea. There are 1, 2, 3, 4, 5, 6 nodes in the tree. There are 3 leaves, and yeah, that I guess is the first part. And then the question is, how do we store this in a computer? Okay, and the answer is we use pointers. Okay, so each node is like its own little struct. So it's like struct node, and it has both data, like int data, which actually holds the 42, the 13, the 55, and then it holds pointers to its children, sometimes also the parent, okay? But definitely you need a pointer to the children, that's for sure. So it'll be node star left, and then node star right, in this particular case of a binary tree. So that is each individual node, and then all you have to do is make a bunch of these things on the heap, chain them together, and all the leaves, those have null pointers. Okay, that's how you know you can't go any further. There's nothing left. Okay, so that's how we store those inside of a computer. So let me go and make this tree in C++ for you. How about that? Vim trees. So I will make my node struct, int data, node star left, same for right, and then I can make trees. Node star, I don't know, 42, I'll use underscores just to make it easy on me, equals new node, and usually you make the nodes on the heap. Just like you would with linked list. So yeah, you can say 42 nodes data. Well, that's going to hold 42, and then its left and right are going to be some other things. And oh, I forgot that semicolon. Excuse me. So then we need to set its left, and then we can set its right, and those are going to be pointers to other nodes, which I should probably just make up here. Okay, so we got 42, 13, 55, .13's data is 13, and then, I don't know, we got node 55, 55's data is 55. And so that I don't bore you further, I'm just going to skip these other nodes, and we're just going to pretend this is the entire tree. Okay, so that'll make both of these leaves, and they're the left and right child of 42. Okay, so 13 will be a leaf, so its left is null, same with its right, and similarly for the node 55. Oops. I want to change this to 55's left and right being null. And then finally I can say for the node 42, who is the root, 42's left is the address of the 13 node, and its right is the address of the 55 node. Okay, so hopefully this is all coming back to you. I've made 3 nodes on the heap, and I've set their data, their lefts, and their rights. Okay, and 42 is the root. So this has drawn the tree that looks like this. I've skipped these other 2 so that I don't waste your time. Okay, and every leaf just has null child pointers. Okay, and we can traverse this tree if we want to. We can say that, yeah, node star root is the 42 node. That's usually what we do. We usually package this up into a little tree class a lot of the time. Say, I don't know, class tree, and then it has, like, I'm just going to be lazy and say public root. That's a node star, and that's usually the one thing that you put as a member variable of a tree class. It just holds the initial tree. So it holds the root, and the entire tree can be found through the root, right? All the nodes you can get to from the root. So, I don't know, tree t.root equals the 42 node, and now we can traverse the tree using t.root. We can say, we can print out the 55, for example, by going right from the root and getting the data there. Yeah? So I can say something like cout t.root arrow right arrow data. Yeah? That is the hope. And that'll get the 55 node. So let's see if that is going to work. Let us compile and run it. Oh darn. New window. How about that? Hey, alright. So yeah, this is refresher on how to do binary trees in C++. Things are going to, of course, get a bit more fancy in this lab because we are growing as programmers. So let's continue. So that's binary trees. Let's talk about our lab now. So what I have mostly made is the artificial intelligence part of the tic-tac-toe playing system. It's your job to generate the states of the game that you could travel to, okay? And we'll use a tree for that. Because in tic-tac-toe, there's at most, right, strictly less than 3 to the 9 possible game states, because you got x, y, and blank, or sorry, x, o, and blank, and you have 9 squares to fill, yeah? And there are some game states that don't ever exist, like all x's, right, because o needs a chance to play. Okay, so what we'll do in this lab is we'll make a tree of game states to like discover how many ways we could play the game. So initially, the game looks like this, right? It's all blank. And then we're going to assume that x goes first, and then we can make trees that tell us all the different ways how x could make the first move. Okay, the first move could be up here. It could then be over here in the middle. It could then be over here. And you have 9 options, of course. And then the last move can be over there. So there's 9 different children of the root, which is the empty game state. You see where I'm going with this? And then you can make children of these, because then O gets a chance to move. O can move, for example, wherever X isn't. So this is the game so far. Then O could go right here. O could go not there, because X is there. O could go right here, etc. And O could go all the way down to the corner. So you have a bunch of children, 8 children of this node. You see the pattern. So the idea is you're going to enumerate this entire tree because there are a ton of different children. And eventually you're going to get down to like game states where somebody won, perhaps. So like, let's pretend that X won. And those will be the leaves. Okay, so maybe X went here. O had to have gone here if we came from this node. Maybe X went there, O went there, and then X went here. So that's a winning state for X, and there's multiple children here. I hope you see how this is working. You have your top level node, and then each time you play the game, you save the state of the board. Like X goes, and then it's O's turn on this level of the tree, then it's X's turn again, and then all the way down to the leaves, which have no children, and that's where the game is over. Either the board is full or somebody's won. Okay? This is the tree that you will generate in this lab. Okay? So, yeah, that's my example. And the whole point of generating this entire game tree is that we can search through it. We're like, okay, if this is the current state of the game, let's traverse that subtree to figure out the best move, okay? Because there are ways of doing that. That's more the topic of an artificial intelligence class, but I'd be happy to talk about the strategy that I've implemented in this lab for you, okay? So that is the idea. The main job of you in this lab is to generate this tree. After that, it's mostly smooth sailing, okay? So not a ton of code that you write. I've written most of it. But again, it's a lot that's been done and a lot that you have to understand. Okay, so let's look at the code and go from there. So here is the starter code. You have a bunch of files, and the most important ones are going to be these three. You don't really have to look at test tic-tac-toe, but you can see like what's being checked very easily there. So let's go ahead and look at tic-tac-toe.h maybe. And we'll start with that. So here's tic-tac-toe.h, and here is how we're going to represent the tree, okay? So the tree for all the game states is called game tree, and it holds the root, okay? And we're going to use fancy shared pointers instead of normal ones because we know better, okay? So shared pointers to one game tree node, that is the root. It's as if I said game tree node star. It's just being managed for me, right? And then we have a bunch of methods that I'll talk about. And inside of every game tree node, we have to store things, right? We need to store the current state of the board and then also all the little children. So we do that. So we hold the board and then all the next moves that you can go to. And that is going to end up being a set of things, okay? It's a set of game tree node pointers, okay? That's how I want you to read it. And it's being ordered in a specific way so that I can grade it, so you don't have to worry too much about this thing. But it's a set of pointers to nodes, okay? That will be your children, okay? And so a leaf in this world is no longer null, it's just the empty set. And maybe I should write that. So a leaf in a leaf game tree node has an empty next moves set. Okay, that's how you represent the fact that you don't have any children. You just keep this set called next moves empty. Okay, and then finally, what's a board? It's just a fancy way of saying this. Okay, it's just a vector of vectors of characters. It's a 2D vector of chars. Okay, that's all. So each row is its own little vector. And so, for example, this particular board would be represented as the following. It would be represented as this vector. Okay, are you ready? It would be, what was it? Blank, and that is represented by a dash. Oh no, why? I've appeared to lose all my drawing capabilities. No, there it goes. So we've got dash. What about this? Dash XO. It's a bunch of characters, remember? That's the first vector. It's a vector of vectors. And then we have OX dash. And then finally we have dash X dash. Okay, so that's the vector. of vectors of characters that represents this game board. You can just draw some lines here and it should be pretty self-explanatory. Yeah. So that represents this tree right here, or this tree node. That's the board for that node. Okay, so that's how you keep track of all your game states. Yeah. Hopefully that's all making some sense. And then finally, that brings us to tic-tac-toe.cpp. So what you're going to be doing is not a whole lot. So the constructor is going to do most of the heavy lifting. It's going to start out the first node. It's going to make an empty board, and that is all dashes, of course. And then it's going to set the root of the game tree, which holds the blank board. And so it'll set the board to be empty. It'll set itself to be the root, that tree node that it just made. And then it's going to call BuildTree on the root with the first player. We're going to assume X always goes first. Okay? And this is where you come in. Okay? BuildTree is going to be something that you write. And I guess I might as well go over it first. Okay? So what you're going to do with BuildTree is you're given this tree. This function is recursive. It's a method, but it's really being used as a function. It is recursive in that it takes the current subtree that you're trying to fill. You're trying to see where you can go with this game. That's represented by this current root. And then you give who is the next player. Okay? So for example, if you are, I don't know, if your current subtree root looks like this, X went first, then O, then X, then O. If this is your current subtree root, it's your job to fill in the children, right? Which are right now potentially empty. It is whose turn? It is the player that is going next is going to be X, okay? So then player would be X. And then it's your job to fill in the children, okay? Fill in, figure out the next moves, and then recursively build the trees for the children. So you're going to call BuildTree inside of itself after you've generated all the next moves that you can make, okay? So that's essentially all you have to do for BuildTree. You need to figure out the next moves that you can make from where you are, which is given to you by generate next moves. You're welcome. So you give it the current board and the current player who's about to play, and you have those. And it'll give you back the next boards that you can make. It tries all the different possible next moves. Okay, so you'll be calling this. Whee. So that's the first fix me. You're going to generate the next moves that you could make from this particular state. Then, once you have them, you're going to start building game tree nodes for each of those, because that's how you represent the children of this tree node. All right? So for each board you can go to, you need to make a tree node for that child, set the board, recursively build the tree by calling BuildTree with that thing as its new root, and then you want to add this child to the next moves set, which you will then put inside of the subtree root. Okay? So this is just taking a single node. This is your node. It represents this and giving it children. Okay? Giving it children and populating those children nodes. Okay? And the recursion will do the rest of the job for you. Okay? That is the hope. So each of these fix me should just be about one line, and that will build this game tree that represents where you can go from here. Okay, so that is probably the hardest function. It's not a lot of lines, but it's a lot to wrap your head around. So please yell at me if you have any questions. You'll be using generate next moves. And then the next two methods that you're going to write are quite easy. Okay, so the game revolves around figuring out when we can still continue. Okay, so you need to figure out the winner of a tic-tac-toe board, which is something I give as a lab in my CSCI 40, actually. So given a board, which you know what it looks like and how it's represented, you need to give back an answer of who is the winner. Okay, so that one is X. And in other cases, like the game isn't over or it's a tie, you give back a question mark. Okay, So that is what winner does. Okay, so that is being used in a bunch of different places. Let me see if I can show you. So winner is actually being used in generating the next moves. It figures out if it's already over. And same with calculating a special score, which is used in the artificial intelligence engine that I've implemented. Winner is being used all over the place. And so this is going to be hopefully a quick little method where you take a board, which you know is just a vector of vectors of characters, and you then go and figure out who won. You give back the character of who won, okay? If the winner was X, you pick X. If the winner was O, you pick O. Otherwise, if there's no winner yet or it's a tie, you return the question mark character, okay? That's all you have to do. So make it work like that. And so you're going to have to check for winners all the rows, all the columns, and then both diagonals. Okay, that's how you figure out who's the winner in tic-tac-toe. And so that should be a quick little method. And then finally, this is going to be probably the second hardest one, but hopefully not too difficult because breadth first search is something we went over in class and I gave you pseudocode for. So it's not really necessary for like figuring out the best move, but it's a good exercise, okay? Because it's probably the hardest traversal to write. You got to use a queue and all that fancy stuff, right? So what I want you to do is for breadth first search, you're going to be given the root of the tree, way down here. Or actually, you're going to start from the root of the tree. You're not even going to be given it, okay? So start from the root and traverse the game tree, okay? Traverse the root of the game tree starting at the very tippy top and create a list of all the boards you see in the order in which you see them. Because remember that a breadth first search goes in, like, if this was the tree, it goes in level order, right? And so your breadth first search is going to add all of these nodes in this order, 1, 2, 3, 4, 5, 6, 7 to this list, okay? You're going to pick out the little boards and add those to this list. And so that's how I check if you did it correctly, okay? So that is breadth first search. You just run a traversal of the entire game tree that you generated, okay? So those are the 3 methods that you will be writing for this lab, okay? BuildTree is the hardest, BFS is probably the second hardest, and winner is the easiest, all right? So do yell at me if you have any questions. There are a lot of comments, and there's a lot of extra code that I wrote to do cool stuff. I'd be happy to answer any questions you have about any of it. So let's quickly go to the write-up, which we don't really have to stay on very long because I talked about most of the stuff. So you're going to get the code. It looks all like this, and you will be implementing those parts that we talked about of the game tree class. Probably the last piece of information that you need is how do you like test yourself. So what you do is you compile with make test tic-tac-toe, and then you run it like this with /test tic-tac-toe and then run tests, okay? This time you don't just say /tic-tac-toe or test tic-tac-toe. You have to say run tests as well, because if you don't do it, it'll run a different thing, okay? So you want to run the tests as you're developing it, and so that will run all these fancy 4 tests that I've made, which test that you implemented the game tree, it's being generated correctly, and like it's picking the winner properly based on what I have implemented for you, and then that you're doing the BFS correctly. That is those are all the tests, so get those passing, and then once you have them passing, you can do a fun thing. Let's see if I can go to my solution quickly. So this is what run tests will look like. Build the game tree and run the tests on it, and you should see passed. And then, if you run test tic-tac-toe by itself, here's what you can do. After you've got it working, you can enter the board in this kind of style, where you give 9 characters, and make sure you keep track of like whose turn it should be. x, x, o, 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 and x went first, so it should be x's turn. So it's x's turn. And then it'll use the game tree to search for the best possible move. Okay? And it looks like the best possible move for... Oh, sorry, the game's over. Excuse me. Let's do the one before it. Sorry about that. There are no best next moves, of course. X dash dash, X, X dash, O, O dash, and it's O's turn this time. And so it'll say, oh yeah, definitely go there, O. And that is, that's what it's doing. It's cool stuff. Okay, so that is, I think, everything. Yeah, you have your own little artificial intelligence engine that can play tic-tac-toe. Okay, don't try and take over the world with it. So you'll only be turning in your implementation file because that's what you're changing, and yeah, get those 4 tests to pass, and that is your lab. So please do yell at me if you have any questions. Again, it is a lot to take in, but it's relatively few lines of code, okay? That is becoming a common thing in this class, isn't it? So that is officially all I have for you. Good luck, and I will see you next week.